Hello, chemistry students. We're moving on to our last really big topic. The last three sections in this unit deal with nuclear transformations, nuclear chemistry. We're going to start by looking at radioactive decay. We're going to look at alpha decay, beta decay, gamma decay. We're going to look at how we write nuclear equations and something called particle bombardment. Let's do a very quick review. We've had this earlier this year, all of these things, but I want to make sure you remember them. The nucleus in the atom is made up of what we call nucleons. When you see that word, it's referring to the neutrons and the protons. The atomic number, oftentimes in nuclear chemistry, that gets designated as the Z. It's the number of protons in the nucleus, the atomic number. The mass number oftentimes is symbolized with an A, and the mass number is the sum of the neutrons and the protons. Remember that. Isotopes, remember what isotopes are? Atoms with identical atomic numbers. The Z is the same. They have the same number of protons, but they have different mass numbers. So their mass numbers will be different. What is a nuclide? That's a new term. A unique atom, it's represented by this. So a nuclide would be just a unique atom. They're called nuclides in our nuclear chemistry here. And we represent them with X being the symbol of that nuclide. So if it's a chlorine, this would be obviously capital C, lowercase l. And then A is written in the top as for the mass number. And the bottom number, Z, represents the atomic number. Here is an overview of what we are going to look at. I'm not going to go into all of this right off the bat, but we're going to look at every single one of these different types of decay. We're going to look at alpha decay. That's an alpha particle. We're going to look at beta decay. That's the beta radiation that gets emitted. A positron emission, electron capture, gamma emission. These are different kinds of decay. These are their general equations, and these are sort of the model, the picture in your mind that you can think of when these kinds of decay happen. We're going to look at each one individually and then sum it up at the end. So we're going to look at one kind of radioactive decay first. Before I start, I realized I need to tell you, what is radioactive anyway? Not all nuclei are radioactive, but many of them are. And when they are radioactive, it simply means that they spontaneously decompose, forming a different nucleus and producing one or more other particles. So we're going to look at those different types. The first type of radioactive decay is this alpha particle. This is the alpha particle. It's in essence a helium with a mass of 4 and 2 protons in it. So alpha decay is something where we would have our radioactive element right here, our radioactive nuclide, and if it decays by alpha particle emission, it's going to emit or give off an alpha particle right here. There will be something else that's also formed, another nuclide. And how do we know what that other nuclide is going to be? Well, if you look at this equation, you know that if I start here with this nuclide, and I tell you, you're going to, this nuclide decays by alpha radiation, you know you're going to produce an alpha particle. You write that alpha particle over here. You know that the sum of these two atomic masses must equal this atomic mass. So you know that this must be 235, because 235 plus 4 equals 239. You also know that the sum of the protons also has to be conserved, right? We'll conserve matter here. So this must be 92. Because 92 plus 2 will give us 94. And from there, you can look on the periodic table and see that 92 protons, that's how many protons is in a uranium atom. So this is the uranium nuclide. Now here's an example, right? What is the nuclear equation for this nuclide producing an alpha particle. So I went ahead and wrote what we need to write down to do this problem. I wrote neptunium, the neptunium nuclide here with the atomic mass and the atomic number, and I wrote that it gives off an alpha particle, which is helium, with a mass of 4 and 2 protons. Now I can figure out what needs to go here, right? I know that I need 93 protons total. I have 2 in that helium, so I know that my new nuclide must have 91, because 91 plus 2 is 93. I also know that my new nuclide must have a mass of 233, because 233 plus 4 will give me 237. Now I can look on the periodic table. When I look on the periodic table, I see that protactinium has 91 protons. Its symbol is Pa. So here now I have just written my nuclear equation. Now let's look at beta particle emission. Might be good to know when we talk about a beta particle emission, what is a beta particle? And a beta particle is essentially a particle that is so tiny we call its mass 0, kind of like an electron. It also has a -1 charge, kind of like an electron. The interesting thing about beta particle emission, and you're going to see this as we write the nuclear equations for it, the net effect of beta particle emission is that it changes a neutron from the nuclide into a proton. And we're not going really any more into depth than that. We're just going to look at how to write the basic nuclear equations. Another thing to mention is I am not talking about neutrinos or antineutrinos or anything else. There are other things going on in these reactions as well. We are just looking at the very basics of these nuclear reactions or nuclear equations. So let's look at an example of beta particle emission. Here we have tritium. It's a very heavy hydrogen nuclide. It has 1 proton, and its mass is 3, so it also has 2 neutrons in it. And it decays by beta particle emission. You can see that when it decays, we write the beta particle over here. We have to make sure that everything on the left side equals everything on the right side, just like we did for the alpha particle. If our mass is essentially 0 for the beta particle, our mass then on this new nuclide will have to be a 3. If we have a -1 charge on our beta particle, we will need to have 2 protons on our new nuclide to make this balanced. 2 minus 1 is 1. We have a total of 1 protons on the left. So when we look on the periodic table, we see that helium with a mass has 2 protons. So this nuclide is a helium nuclide, and that's how we will balance it. Now you try, see if you can write the nuclear equation for bismuth 214 producing a beta particle. Pause the video, see if you can do it, and then I'll do it together with you. Okay, probably you got this right, but let's just walk through it real quick. Here's bismuth 214, it has 83 protons, mass of 214. It's going to produce a beta particle, which it looks like this. What will we have for our other nuclide? We know that the mass will have to be 214 because 214 plus 0 on the right side gives us 214 on the left side. And we know that the number of protons on the right side, needs to be 84 because 84 minus 1 gives 83. Now those match. We can now write our nuclide because we can look at the periodic table. We can see that the element that has 84 protons is polonium. And that is the symbol for polonium, and that's our nuclear equation. Now let's look at gamma decay, and this is a really easy one because a gamma ray essentially has no mass and no charge. So I'll write what that looks like, the symbol for that. So here we have our symbol for a gamma ray. It's essentially a high energy photon of light, and a nuclide that's in an excited nuclear energy state can release excess energy by producing a gamma ray. Oftentimes, gamma ray emission accompanies other types of decay. For example, if uranium-238, it degrading by alpha particle emission could also produce. It also does produce 2 gamma rays. It has no net effect on, it does not change the atomic mass, it does not change the atomic number, because those are both 0. So it's not very interesting for the nuclear equations, but they're often just a way for the nucleus to get rid of excess energy. Now let's take a look at positron decay. A positron, we should look at what that is first, is essentially the same as an electron, but with an opposite charge. It has 0 mass, it's very tiny, and it has a charge of +1. Oftentimes the plus is omitted, you'll just see a 1, but it's a +1 charge. That's called a positron particle. When positron decay happens, a positron particle is given off. So again, just applying the same types of principles that we've applied before, you can balance your nuclear equation in the same way. Sometimes you will see a positron written like this, as a beta particle with a 1 charge. There are different ways of writing that. I'll probably usually refer to it as an electron with a +1 charge and 0 mass. So let's see if you can write the nuclear equation for potassium-38 decaying by positron production. Pause the video and see if you can do that. Okay, here's our answer. I filled out what we have, what we know, potassium-38 as the mass with 19 protons. Here's our positron is being produced. So what do we need on the right side of the equation? Well, we need the mass to remain 38 because 38 plus 0 is still 38. And what are we going to write for the number of protons? Well, we need 18 protons on the right because 18 plus 1 gives us 19 protons on the right side. There are 19 on the left. So our element here, when we look on the periodic table, what element has 18 protons? Argon. So our nuclide that is produced is argon. Let's look at the last type of radioactive decay that we are going to discuss, and that is electron capture. Electron capture is simply the process in which one of the inner orbital electrons is captured by the nucleus, and that's represented here, an electron. Gamma rays are always produced with electron capture, even though they're not written here. These are just examples of electron capture. So this is a different nuclear equation that we're going to write than the other ones because the electron is captured by the nucleus. So the electron will appear on the left side of the equation because it's captured, as you can see right here. So when you balance this nuclear equation, make sure you write the electron on the left side. See if you can write the nuclear equation for gold-195 decaying by electron capture. Okay, I wrote the basics for our equation, the gold-195, electron capture, so the electron goes on the left side of the equation. There's some gamma ray being produced there that you can write. And what is the other nuclide that will be produced? Well, I know that the mass will have to be 195 because I have 195 for the mass on this side plus 0. and I have no mass over here, so I have to have 195 for the mass. And what will the number of protons be? Well, no, it must be 78, right? Because 79 minus 1 is 78 on the left side. I must have 78 on the right. So what will my nuclide be? When I look on the periodic table, I see that 78 protons gives us platinum. So go ahead and write my plus symbol there, and that is our nuclear equation for decay by electron capture. So one thing to note, oftentimes a radioactive nucleus cannot achieve a stable state through a single decay process. So it will undergo what we call a decay series, and I don't have this written on here, but decay series would just be a series of decay processes until it achieves a stable or a non-radioactive state. And that is just something to keep in mind. Another important idea when we talk about nuclear chemistry is the idea of a nuclear transformation, where we're changing one element into another intentionally. In the early 1900s, a scientist by the name of Lord Rutherford observed the first nuclear transformation, where he found that bombarding nitrogen with alpha particles could produce the nuclide oxygen-17. I'll write that down. So there are a lot of different nuclear transformations that can occur. This was the first one that was witnessed. Here's another one, uranium being bombarded with a neutron. And all kinds of different nuclear transformations that can occur when nuclei are being bombarded with different particles, alpha particles or neutrons. So when particle bombardment happens, we can have neutron or positive ion bombardment, alpha particles. Other particles can be used as well. They have to be moving at extremely high speeds. So particle accelerators have been built to achieve this. Also, this is just a table showing how the synthesis of some of the transuranium elements have occurred. Since 1940, the elements with the atomic numbers 93 through 112 are called the transuranium elements, and many of them have been synthesized via particle bombardment. And this table just shows some of those examples. It's kind of interesting to look at if you want to pause that and take a look at some of these nuclear transformations. Here are some practice problems for you to do. I'd like you just to remember how to practice writing balanced nuclear equations for each of these, because you'll definitely be responsible for knowing how to do all of that, and the answers are on the following page. Here are the answers. Here are a couple of advanced ideas. Read through some of those, some things we haven't talked about. And if you have other questions or other interests, ask those questions, do some research, come and tell me in class, and I look forward to seeing you.